In this video, we're going to explore the commutative property of multiplication. You might have heard of this property before in connection with addition. Both multiplication and addition are commutative. We'll explore the meaning of this in a moment. If we represent 3 times 4 using objects, it could look like this. 1 group of 4, 2 groups of 4, 3 groups of 4. The way we represented it here is known as an array. This is a rectangular formation made up from rows and columns. In this particular array, there are 3 rows to represent the 3 groups, 1 group, 2 groups, 3 groups, and there are 4 columns to represent the number of items in each group, 1 column, 2 columns, 3 columns, 4 columns. If I counted all of these items up, I would have 12 objects altogether, so 3 times 4 equals 12. Using this information, we'll explore what the commutative property is. Let's look at one way of creating groups from my array. Grouping by the rows, I could describe this as 3 groups of 4. Here's 1 group of 4, 2 groups of 4, and 3 groups of 4. 3 groups of 4 equals 12. This reflects our equation above. 3 times 4 equals 12. If we make a copy of the same array and then look at what happens if we rotate it by 90 degrees or turn it a quarter turn, there's no difference to the number of objects in the array. We haven't added any and we haven't removed any. There are still 12. Pause the video and try to think about what is the same and what is different about the rows and columns, as well as the total number of objects in the 2 images. After you've had some time to come up with your own ideas, resume the video. We can see that the original image had 3 rows and 4 columns. In the second image, we can see that there are now 4 rows instead of 3, and 3 columns instead of 4. The number of rows and columns in each image has switched around as we rotated the image through 90 degrees. We've seen that if we group the objects by rows, the first image has 3 groups of 4, which equals 12. Which we can write in an equation as 3 times 4 equals 12. If we group the second image by rows as well, the groupings look like this. Pause the video for a moment and think about how we can describe these groups in words and using an equation, as we did with the first image. Resume the video when you've finished. In words, we might describe this image as 4 groups of 3 equals 12. As an equation, we might record this as 4 times 3 equals 12. In both images, although the factors 3 and 4 have changed position, the product, 12, is still the same. This is the commutative property. In multiplication, if you change the order of the factors, the product will remain the same. To understand this further and see it in a different way, we'll explore it using cubes along a number line. In the first set, we're going to put together groups of 3 cubes at a time. 1 group of 3 is 3 cubes. 2 groups of 3 is 6 cubes. 3 groups of 3 is 9 cubes, and 4 groups of 3 is 12 cubes. So 4 times 3 equals 12. In the second set, we're going to put our cubes into groups of 4. 1 group of 4 is 4 cubes, 2 groups of 4 is 8 cubes, and 3 groups of 4 is 12 cubes. So 3 times 4 equals 12. Again, we can see that when we're multiplying, it doesn't matter which order the factors are in. The product is still the same. In this example, the factors were 3 and 4, and the product was 12. So in the first image, 3 times 4 equals 12. In the second image, 4 times 3 equals 12. So we can say that 3 times 4 equals 4 times 3. If they're both equal to 12, then they must be equal to one another. We'll look at one more example just to see this in terms of the physical space that something is taking up. We'll use a set of coloured rods for this, and for this video, the white rod will have a value of 1. This means that the pink rod has a value of 4, and the dark green rod has a value of 6. Let's show 6 lots of the pink rod. As a reminder, the white rod has a value of 1. Let's show 6 lots of the pink rod, i.e. 6 lots of 4. 1 lot of 4, 2 lots of 4, 3 lots of 4, 4 lots of 4, 5 lots of 4, 6 lots of 4. I can write this as an expression like this: 6 times 4. Now let's show 4 lots of the dark green rod, i.e. 4 lots of 6. 1 lot of 6, 2 lots of 6, 3 lots of 6, 4 lots of 6. I can write this as an expression like this: 4 times 6. Pause the video for a moment and consider what's the same and what's different. We can see the images look different. In the first set of pink rods, there are 6 rods, and each rod has a value of 4. In the second set of dark green rods, there are 4 rods, and each rod has a value of 6. If we look at the expressions, we can see that the order that the 6 and the 4 appear are switched. The first expression says 6 times 4, and the second expression says 4 times 6. If we lay the 2 sets of rods on top of one another, we can see that they occupy the same amount of space. Even without knowing what the total is, we know that the value of the sets must be the same. So what is 6 times 4, or 4 times 6? You might have worked this out already, but if you haven't, pause the video and try to figure it out. We'll bring the white rods back in to help us, and we'll count in 4s, although there are many other more efficient ways to work this out. 4, 8, 12, 16, 20, 24. So 6 times 4 equals 4 times 6, which equals 24. So we can say 6 times 4 equals 24, and 4 times 6 equals 24. So as a summary, here are the things we learnt about the commutative property. The order of the factors doesn't matter, the product will be the same. So 3 times 4 equals 4 times 3. This is useful because if I know one multiplication fact, I can use it to instantly know another fact. For example, if I know 3 times 4 equals 12, I also know that 4 times 3 equals 12.